Another situation we can have is what we call an RL discharging circuit. The circuit's not valid anymore. A discharging circuit is one in which the inductor had been connected to a battery, so it had current flowing through it. But then there's a switch in the circuit that disconnects it from the battery and connects the inductor through some other resistance. So this side of the circuit's gone. The battery's gone. The battery had to be there in the first place to make current flow, but now we've disconnected it from the battery. The inductor liked having that current flow. It likes whatever situation it was just in.
So it seems very indecisive.
It just doesn't like change, basically. Now, I know it doesn't really have real feelings, but it's a good way to think about it. So the inductor tries to keep that current flowing. And the way, where it gets its energy from is the magnetic field that's in the coil. That magnetic field is able to induce the current, because the magnetic field is going to change, which induces the current in the circuit. So the net result of the current in our circuit versus time is that the current, initially the inductor is successful and it creates whatever initial current it had. So it induces that initial current. But as the energy dissipates, so does the current decreases with time. So the inductor actually makes it so the current doesn't just automatically drop to zero. It decreases. Now, yes, it would. Yeah. As the current flows through the resistor, yes, it will generate some heat. Some sort of heat. Exactly. And so the energy disappears, basically. It's not that it's not conserved, it's just generated into other forms that we can't maintain. So if we look at Kirchhoff's loop rule here, the voltage drop across the inductor plus the voltage drop across the resistor have to add to zero. There's no battery anymore. The battery's not connected. So that means whatever voltage drop the inductor has at any instant in time, the resistor has the same voltage drop, but opposite in sign. Well, we get an equation for current in our circuit as a function of time. I naught represents whatever initial current the inductor had before that switch is flipped. It doesn't have to be Imax. You don't have to leave the switch connected to the battery long enough to reach Imax. That's why I'm calling it I naught. It certainly could be Imax that it had. But I'm going to call it I naught because it doesn't have to be what the max was. Just an exponential function. The current decreases with time. And tau is still L over R. So whether it's RL charging or LR discharging, the time constant is still L over R. The difference we have is the equation we get for current as a function of time. So the current will decrease. And voltage drop across the resistor is still IR. Voltage drop across the inductor is still L di dt. So similar types of questions. You could ask how long it takes for the current to drop to a certain value. I'm not going to do one just because it's very similar to what just done.
Cross that I naught, right?
Yeah. And all circuits, whether you want them to or not, have some inductance. And so you'll always have this effect as you power down an appliance. How quickly it happens depends upon the size of the inductance and resistance in your circuit.